Polynomial functions of higher degree. Using transformations, coefficients, find and use the real zeros of a polynomial function. Aid. Intermediate value theorem. So a graph of a polynomial function. In this section, we studied kind of the basics of the graphs of polynomial function. The first is that a polynomial function is continuous. Essentially, it doesn't have an endpoint. Well, it doesn't have an endpoint because it's going on forever. Most higher degree functions do. But there's no gaps. There's no point if I were to graph it and put my, kind of we're drawing the graph where I would have a spot where I'd pick the pin up. It's continuous. That's really what kind of the one way they describe continuous functions is it keeps going. There's no breaks, holes, or gaps. So we don't have a function that does this, hole, and continues. This is a hole. That's a gap because there's a space in between. There's some spot where I pick the pin up, move it over, and keep going. There's no breaks. There's no discontinuity. Discontinuity. Breaks, holes, or gaps. But that's it. So it just continues on forever. Normally, the way we say it is if you can draw the whole graph without picking your pin up, then it is. And that's excluding when you start it and end it, because you put it down, you go all the way, now you've done. So as long as you don't have to pick it up and draw a circle, leave a hole, it is continuous. This is not continuous because there's a gap right there. This is because it's smooth rounded turns. We continue to draw the whole thing. It's continuous. To the function this here, which has a sharp turn at 0, 0 is shown in the figure. The graph of polynomial function. So a polynomial function cannot have a sharp turn. This here, where it just changes direction immediately. Polynomial functions of degree greater than 2 are more difficult to analyze than these here because there's more to it. However, using different presentations, you can make a reasonably accurate sketch by hand, but we have a graphing calculator. There's no reason for it. X squared and x cubed. X squared and x to the fourth are very similar to each other. There's just slight differences in their graphs. It's not going to be a whole lot. But the graphing calculator will be able to kind of tell the difference. Greater than n flat near the origin. So if I wanted to sketch these, graphing calculator, there's no reason not to use it. Okay. So the first one here, negative x to the fifth, gives us that graph. That's just what the graph would be. And it's flatter more at the center because it's a higher degree of power. And it's almost like x cubed, but it's flipped. And then we could have this one here. Leading coefficient test. In example 1, note that the rise and fall, whether the graph of polynomial function eventually rises or falls, can be determined by the function's degree, even or odd, and by its leading coefficient, positive or negative. Now, what they call the leading coefficient test, we called end behavior. If you remember this last year when we talked about end behavior as it goes left to right, up or down, as approaches positive infinity, negative infinity. So when n is odd, we're talking about odd degree. So the highest exponent, the biggest exponent attached to a variable is odd. It's considered odd. It's going to do one of two things. It's going to be this one or this one. If n is odd and the leading coefficient is positive, so whatever it is, so x to the fifth, or you can say 6x to the fifth, or whatever it is, odd power, positive number. The graph falls to the left and rises to the right. So it falls to the left. It goes down to negative infinity to the left. It goes positive infinity to the right. That's it. Now, if we had something like negative 6x to the fifth, the leading coefficient is negative. It rises to the right and falls, or rises to the left and falls to the right. You want a positive infinity to the left, negative infinity to the right. So when we have odd degrees, it's always going to be opposite. One's going down, one's going up. Or one's going up, one's going down. One's falling up, One falls to the left, rises to the right. So one's falling, one's rising, or one's rising, one's falling. It's going to be opposite. Now with even, so say 6x to the fourth, the graph rises to the left and right. It's going to go in the same direction. If it's even and positive, it's going up. If it's even and negative, it's going down. Now, if you notice on the other one too, they have this here in the middle. That's really saying anything could be happening between these points, but eventually at some point it's going to go up and up both ways. And so it's going to do a whole lot of stuff here in the middle, but eventually it's going to go down and down on both sides. Yeah, so odds are opposite, evens are the same. So let's look at this one here. Negative x cubed, so this is odd and negative, yes? So it falls to the rises to the left. Falls to the right, rises to the left. So we can go back to odd negative, rises to the left, falls to the right. Let's see here. And there's the graph. Rising to the left, rising to the left, falling to the right. So that's the first one. Next one is what? Even and positive, yes? So Zach, what would we be doing? So to the right, it would. Right. Mm-hmm. So it would raise. Left, it would. Yes.
Oh, yeah, even.
Evens go in the same direction. Now you're probably wondering, why is this important? Yes? I mean, it'd be kind of helpful to know. And I've mentioned this before, but you've probably forgotten because this is some of the little details that we talk about in Algebra 2. About 80%, if you remember at least 20% of it, it's probably a good day. But when we look at this here, we know that eventually they're both going to go up, yes? So, let's say, because again, that little graphing calculator, can it show you all the x values and all the y values on the table? Well, no, because it only goes from negative 10 to 10, yes, on a standard window. They were looking at an even function that has a positive a value, okay? So you see it come in, and no, let's change that just a little bit. And then it takes off this way. Well, that's what the window shows us, yes? So what do we know about the end behavior? It should still come back up. So that tells me that there's some value over here where this line will recross, yes? So what am I looking for? I need to look in this direction. I can look at the table to see where does it cross. And I know that there's going to be another point where this crosses the x-axis, yes? So when we're solving these, I'm solving these, I can know, okay, it's going to come back up. There's another value. So let me back up. So if, let's not say even, let's say odd. What do we? So odd and positive, yes? It rises to the right and falls to the left because it's always going to come up. Because if it's odd and positive, it's going to, from left to right, it's going up pretty much the whole way. So that means at some point, this is going to come back down. I'll look back at these here at the original ones. Odd, you notice it's pretty much it's going up. It might do some weird stuff in the middle, but we're starting down a negative and then going to positive. Odd and negative, we're starting at positive and going negative. It's going down. Even, positive, happy, because they both end up in kind of like a weird smile. Negative, both going down as frowned. And that's it. So it gives us this idea of what the graph should look like. Okay? And especially, even if it's a U shape, we see for even and positive, they're both going up. The only way that they come back down is if they come back down on both sides. So if you notice one is just took off to the left, well, most likely it's just going to take off to the right. It's not going to. Does that make sense? So it gives us an idea. It gives us a picture. That's really what this is going after, is a picture. So the last one is odd, positive. So left is a fall and right is a raise. Because again, it's pretty much going up. So it's falling to the left, rising to the right. Questions on this here? Now we did it a little bit more actually technical, because it'd be as f of x approaches, or as x approaches negative infinity. As we go to the left, f of x is approaching negative infinity. The y values are going down. And as x approaches infinity, f of x approaches infinity. X is input. X is the values we plug into the function, yes? As x approaches negative infinity, as x gets smaller, so we're moving on the left side of the x-axis. As we're going left, it falls. It's going to negative infinity. As we go to the right, it mathematical, technical notation, what the book is doing. That's fine. There's just more than one way to write it. Questions on this here? First one, second one I did. And this one here, falls to the left, rises to the... Now, they can do a whole lot of stuff in the middle, but eventually it's going to meet that. It's eventually just going to take off to the right and go down to the left. So it gives us an idea of what we're looking for, or what we should see. That's what this is helpful for. Note that the leading coefficient tells you only whether the graph eventually rises or falls to the left or right. Other characteristics of the graph, such as intercepts, minimums, and maximums, must be determined by other tests, because it's only telling us how it ends. How it's going to start or how it's going to end. Zeros. It can be shown for a polynomial function f of degree n. The following statements are true. The function f has at most n real zeros, where n is the degree. So if we have a degree 2, how many real zeros do we have? 2. If it's degree 5, we have 5. Now it says at most n real zeros, yes? So this is how many it could have. Doesn't mean it's how many it will have, yes? Because we had some, this one here. So since it's degree 2, how many zeros should it have? 2. And when we solve it, we get that this x is equal to plus or minus 1. So we have 2, yes? But we also could have the case for a quadratic degree 2, where the values of x are x equals 2. And that's it, just 2. But again, we should have said we had how many? 2. But in that case, we have one unique solution. Because it can work out that we have the same intercept or the same zero more than once. So we can have the 0, 2, 3, 4, 5, 6, 7, 8, 9 times. It can be repeated, so it doesn't mean it's restricted to it. It's just we might not have any unique zeros. The graph has at most n minus 1 turning points. Turning points are also called the relative minimum or relative maxima. Maximum are points at which the graph changes from increasing to decreasing or vice versa. So where it turns. Turning points. It's where it turns from increasing to decreasing. Okay? And vice versa. Finding the zeros of a polynomial function is one of the most important problems in algebra. It's just finding them. X is equal to A is a zero of the function. X is equal to A is a solution. Same thing. X minus A is a factor of the polynomial. Well, we can use that to find the solution. That's another way to say it. Finding the factors. Or x-intercepts. These are all the same thing. We're talking about the same thing, but just meaning, different meanings or different ways. Find all the zeros for this here. Then determine the maximum number of turning points of the graph. Well, that's the easiest part. Maximum number of turning points is the degree minus 1. So what's the degree? 4 minus 1 is? It's going to turn at least 3 times because even and negative, yes? So we're starting from coming down here, yes? Because it falls to the left and right. So if I'm coming up this direction and I turn once, and I can go back down, yes? Because that would work because, again, odd, it's going to go in the same direction. They're both going down. So I turn again. Well, I'm going this direction. I'm going the wrong way, yes? So what do I have to do? I turn back down. So this is it here. So do you notice for even, 1, 2, 3, it's always going to be an odd number for even because anytime I add a turn, I've got to add a second one to it because it's got to come back down. So there's that. Now, solving. Really what we're wanting to do is find out when this thing is 0. Now, we've gone, in Algebra 2, we went over many, many different ways to solve it. But we're pushing it about a year because we did that last fall is when we covered this. Now, one of the big things we learned or went over is getting this to a degree 2. Yes. Yes. Because negative 2 out of negative 2 reduces to 1, yes? If I pull 2 x's out, I'm left with 2. I essentially pulled everything out and a negative, so it changed the plus 2x squared to minus 1. Okay? Now, the reason Zach did that, or the reason you did that, trying to make sure to leave names out of this, is because we're reducing it to a power of 2. Because we know how to solve quadratics. We know how to solve degree 2. It's not as easy to solve degree 4. So every method we learned for solving higher degrees above 2 and 3, because there are some tricky 3s that we could actually do, but anything above that, so 4th, 5th, 6th, we found methods to reduce the power. We found methods to reduce the power down to 2. So we have this here. So we notice that there's a greatest common factor of 2x squared. So I pulled it out. I have a quadratic, I have a quadratic. Any two things that multiply together, any sets of things that multiply together that equals 0, means one of these have to be 0. So negative 2x squared is equal to 0, or x squared minus 1 is equal to 0. Now, we could do some more steps with that one. I could divide both sides by negative 2. Well, that's still going to be x squared equals 0. We can take the square root. It's still 0. And we'll get into more of this, but this has a multiplicity of 2, because how many zeros are there? There's 2 of them. And on the graph, it'll kiss I'll say kiss, it'll touch that point and go back. So it kind of kisses the line. I don't know why they use that term, but they have it there. So we have that. Now this one over here, we can use the quadratic formula. We can factor it. Or, is there a middle term? Is there a term with x to the first power? No. So one method I like is the square root method. And this only works if there's not a middle term, a term with x to the first power. Is I move everything over. So I have x squared equals 1. We call it square root method, so. So it was degree 4, yes? How many do we have? 1, 2, 3, 4. We have 4 zeros, we're done. We don't have 4 unique zeros. We have 3 unique zeros, but we do have 4 solutions. And that's it. Questions on this here? This. So see, they factored, is what they did here. They factored x squared minus 1 to this here. And they do the same thing. We have 3 turning points. And this is it here. So as I was saying earlier, it comes down, touches the x, and keeps going. That's 3 turning points. Note that because the exponent is greater than 1, the factor negative 2x squared yields a repeated 0. A factor x minus a to the k, where k greater than 1, yields a repeated 0 with multiplicity of k. When k is odd, the graph crosses the x-axis. And when k is even, the graph touches the x-axis, but it does not cross it. Now, if you notice, that defines anything, any of them. So like negative 1 is an odd multiplicity. It has an odd multiplicity of 1. So we really don't talk about 1 because it crosses there and there. It's odd. But it could be a 3. Odd multiplicity of 3. So if we said x equals 1, x equals 1, x equals 1, so I could have type this into your graphing calculator. Now, when you graph this here, do you get it, Zach?
Yeah.
It crosses at one spot. It crosses at 1, yes? It has an odd multiplicity of 3. Now, you'll notice a lot of the odd multiplicities will do this kind of S curve, the sideways S at it. You won't have too many of a straight line with odd multiplicity. Not always. It might, but not always. It'll have some more of a curve to it for the most part, but as you see here, it has a multiplicity of 3. It has 3 values at that point. And that's what we're talking about, odd multiplicity. And that's it. To the graph, a polynomial function is the fact that a polynomial function can change sign only at its zeros. Because for the y values, if it crosses the x-axis, y goes from positive to negative or negative to positive. So it might be easier if we look at a graph. The y values are positive up here, and they are negative down here. And an x-intercept is when it crosses this line, yes? So if it crosses it, well, here it's positive, positive, positive. Now it's negative. Now we go back to being positive, yes? So whenever it crosses the x-axis, it's going to from positive to negative. between two consecutive zeros, a polynomial must be entirely positive or entirely negative. Because we don't have a number that is negative and positive. It's either negative or it's positive. So what that means is if we're looking at this, so -7, -6, -2, 4, well, somewhere between -2 and 4, it crossed the x-axis. So that means we have a point between those two that would be a solution. And the reason these would come up is if the solution's a decimal or an irrational number. So it's a way to look at a graph or look at a table to see where the intercepts pop up. This means when you put the real numbers of a polynomial function in order, they divide the real number line into intervals in which the functions have no sign change. These resulting are test intervals. And this is kind of the intermediate value theorem comes from this, that if we can take a point here, so 2 points A and D. If we take a point between it, C, well, we can eventually find that point. Intermediate value theorem implies that if A, f of A and B, f of B, A value plugged in, A and it plugged in, B and it plugged into the function, are 2 points on the graph of a polynomial function. Okay, we're good with that. Yes? Such that they are not the same point. Okay? F of A is not equal to f of B. That's saying they're not the same point. Then for any number D between f of A and f of B, there must be a number C such that f of C is equal to D. Between any 2 points, there exists another point on the graph. Okay? So between any 2 points, I take 2 points on this number line, I can find a point in the middle that corresponds to a point on the graph. That's what they're calling D. So between any 2 points, I can find a number in the middle. That's all it's saying. Let A and B be real numbers this here, and then we can take values in the middle. The intermediate value theorem can locate a real zero between 2 points. So what we're saying is I can pick any 2 point and find a point in the middle that would make it true. And it's just taking smaller and smaller intervals. For example, the function is negative when x is equal to -2, so it's negative down here. And when x is equal to -1, it's positive, yes? So there's a number between those 2 points that would give us a 0. That would be one of our intercepts. So it follows that the intermediate value theorem that f must have a 0 somewhere between these 2 points because it has to cross the x-axis. Because there has to exist a point between these 2 points that crosses it. By using this reasoning, you can approximate any of them. We can start making smaller and smaller intervals, getting closer and closer to where that is. These are approximate intermediate value theorems approximate this thing. So we begin by getting the function, we can graph it, and we notice here negative, positive. It has to be somewhere between -1 and 0. Okay, because f of -1 is negative and f of 0 is positive, you can apply the intermediate value theorem to conclude that the function has a 0 between these two here. So let's close the window. To pinpoint the 0, let's divide the interval into tenths and evaluate the function at each point. So that means we're looking at not just these here. So we would have done, like plugging in -0.9, -0.8, -0.7, -0.6, and divided into tenths. Well, hey, -0.8, -0.7, we have negative and we have positive, yes? So it must be between these here. For a more accurate compute function, values between those two and apply the intermediate value theorem. So let's do it again. So we can look at negative 0.89, negative 0.88, negative 0.8, and split that up into tenths and see where those two meet, and then do it again and again and again to get a more accurate thing by continuing this. But that's it, because again, we can keep doing it that way. Now, in the graphing calculator, type this in. Type this into y equals. Now hit second trace and scroll down to 0 and hit enter. Now you should see a little flashing kind of mark on there. Do not use up and down. Use the left arrow because it says left bound, yes? So scroll over to where that point is to the left or underneath or to the left of that spot where it crosses. So I'm going to keep going over here. So I'm to the left of where it crosses. Hit enter. Now it says right bound, yes? Did you get that, Zach? So press left. Yep. So we'll do this here. I'm going to stop the video at this point.